Hey there. So last video, I showed you how I programmed EEPROMs using my trusty Commodore 64 that you can see right here. And today I'm going to do the same thing, but instead of using my trusty Commodore 64, I'm going to be using one of my BBC Micros, which is really cool, actually. I'm brand new to BBC Micros, but I've had a lot of fun figuring out how these things work, writing some basic on them, writing some assembly on them, and it's just been a ton of fun. And maybe sometime I will get around to showing you some of my other vintage computers sitting over here, as well as some couple more that I have in the rest of the house. But for right now, let's get right to this demonstration. Okay, so what does it take to actually make this happen? Well, first you need a trusty BBC Micro. You need an EEPROM programmer, which you can see right there that I have built. And one of the things I also had to build to make this work is an RS423 cable, which is hiding back there, the one that looks really messy with the white and the electrical tape. In fact, I will show you a better view of it. This is the cable I built. As you can see, I've got the words, well, you might not be able to see, RGB with a little arrow on it, pointing in the direction of the RGB connector right next door to it. The reason for that is, as you can see, well, you might not be able to see, but this is a 5-pin DIN in a domino pattern, which means that you can actually plug it in this way, or this way, or this way, or this way. And so you want to be sure to plug it in the right way. Apparently it's not going to harm your computer if you do it wrong, but you want to do it right. And then I wired that into I soldered it into a DB9 serial connector, male connector that's connected into this Max 232 device that then heads over into the EEPROM programmer powered by that, as well as this is the receive line going into pin A0, and then this purple one, which you probably can't see the colors, but the purple one is a transmit line. And so of those 5 pins, we're using 3 of them actually, so I don't use the RTS and CTS for flow control because I could not get that to work with the Arduino. Apparently it works well on the BBC side, but not on the Arduino side, so I had to basically just wire those. I believe I wired them together. Or maybe I just disconnected them, I don't recall. But anyway, so I had to build that cable, which was actually kind of fun to do to exercise my terrible soldering skills. Okay, so I always like to start with a clean, fresh ROM just to make sure that anything weird I see on there is because of something I did, and also that the program that I'm using actually does write it instead of still having the program there from a previous attempt. So I'm going to write out the ROM and then read it back and then do a hex dump to see that I filled it up with basically bytes full of EA, which is the no-op command. So as you can see here, the ROM is completely full of just EA. Okay, so now I'm going to walk you through the code on the BBC micro that I use to both write the assembly that's going to get written to the EEPROM, as well as send the bytes over to the EEPROM writer itself. And so that's all contained in one single program. One of the things that's really nice about the BBC is that you're able to mix basic and assembly side by side, which is super, super cool. And so I'm able to have a single basic program that contains some embedded assembly that you will see right now. Okay, so I'm gonna just list the program, kind of walk you through it step by step. Some of it's going to seem a little foreign if you've never coded on the BBC. It's brand new to me, so I'm probably doing things in a less than ideal way, but it works. So, okay, so walking through this, you see the first couple lines. So when you go to write via RS423 on the BBC, it's basically you're choosing either to write to the screen, to a printer, to RS423, or some combination of all of those. And so this FX3, 4 command in line 20 is changing the output to the screen only. I don't really need that at the start of the program, but just in case I get in a weird state, it'll basically clear that back out and start outputting to the screen. Because as you'll see down the code a little bit, when I actually go to send, I disable writing to the screen while I'm sending to the Arduino. Okay, and so then line 30 you can see with BBC Basic, for the assembly, you actually have to allocate an amount of memory where your assembly code is going to go. And a basic rule of thumb I read is that for basically every operation, so load accumulator, store accumulator, each of those you want to have about 3 bytes set aside for, which would be plenty. So I have 256 bytes set aside, which is more than I actually need. I think I end up using like 62 or something like that, but that's okay. I've got plenty for what I'm trying to do. And then line 40 through 50, you can see there I'm setting up some variables, and these are actually going to be directly referenced by the assembly code. And I'm not going to go into what those variables are or what they do. Follow along with Ben Eater's tutorials on the building a 6502 computer if you want to know more about the code that's in here. But what's really cool is you can see I'm actually creating some variables that contain addresses that I'm going to be writing to on the EEPROM. And then lines 60 and 70, that's kind of some of the magic. And I won't claim to be an expert on what's actually going on here, but I'll do my best to explain it. So you can pass some options to the assembler to tell it basically what to do. There's a number of different settings you can use for opt. And basically there's the first 3 bits are what matters. And so if bit 0 is set to 1, that'll give you a listing of the assembled code. So you'll see that at the end. You'll see what my assembled code actually looks like in memory. Bit 1, if that's set, it reports errors. And so basically any error that you get during assembly, it'll report and stop assembling. And then bit 2, we'll place the assembled code at a different location than where it would typically, and I'll get to that in a moment. But that's part of the magic of what we're going to be doing here. So this assembly is going to actually be done in 2 passes. In the first pass, and one of the reasons you want to do 2 passes on an assembler is you may want to declare, set certain labels that you want to use throughout your code. But you don't want to put those, you don't want to always declare those ahead of where you're using them. That would make your code kind of messier and kind of painful to code in. And so when you do a 2-pass assembly, what you do is it will take a first pass and there will be some errors because it won't be able to find certain labels during the first pass. However, it will still define the right memory locations and the right spot where those labels should be, and it will kind of stub it in. And again, I'm not an expert on this stuff, so I don't want to claim that I completely understand the details of what's going on there. But that's basically the gist of it. And then it takes a second pass and fills it all in, so you're able to actually assemble correctly. And so on my first pass, you can see in line 60, I'm going through 2 steps. On the first step, I'm going to set the option to 4, which is going to basically be, it's going to place the assembled code at a different location. So normally, when you write some assembly code on the BBC, you use this p% variable, which tells it basically this is the location in memory where I'm going to assemble the code. And then any labels, any jumps, any branches, anything will reference based off of that location. And so let's say we were p% was set to 2000, and then we created a few bytes, and then we had a label. It'd be like at 2003 or something like that. However, what's really cool about this is that I'm able to set p% to a different location than I'm actually physically assembling in memory. And so that's really cool because I can actually set it to 0 because that's the location it's going to appear on my ROM. I set it to 8000 because that's the location it's going to get written to in my ROM. However, I don't even have that much memory in my BBC Micro, so I'm able to assemble outside of the memory of the computer because it's not actually assembling it to that location. It's actually assembling it to this O percentage point, which is, as you can see in line 30, I allocated memory at start ASM, and then in line 70, you can see there that O% is set to there. So it's actually going to assemble at the location start ASM, but all of the variables, all of the jumps, everything that's defined down below is going to reference memory as if it was all assembled at 8000. And so these 2 passes on the first pass, again, it's taking 2 passes, but on the first pass, it's set to 4, and so it's still going to do that assembly at a different location than the physical spot in memory, but it's not going to report any errors, and it's not going to give a listing at the end of that assembly, because it's going to have a bunch of errors because I'm creating labels that I may not be using until later in the program. And so the second pass, those labels exist, those memory locations are there. And so on the second pass, it all works. And on the second pass, I'm also going to show a listing at the end so you can see the assemble code. I'm going to report errors so you can see any errors that are encountered during the assembly. And then I'm going to still place the assembled code at 0% rather than P%. And by the way, I'm sure they say something different than 0% and P%. O and P, percent's just the integer location. So anyway, so that's the idea. And so you see in line 60, 4 pass equals 4 to 7, step 3. So I'm doing 2 passes, one with that opt set to 4 and one with the opt set to 7. Okay, and then starting at line, so 70 is where I set the location. So line 70, I set P to 8000 because that's where the code is going to be written to on my EEPROM. And then 0% is set to start ASM. That's where I'm assembling to actually in memory on the computer, and then I just print it out. And then lines 90 through the rest of the screen here, this is the actual assembly, and I'm not going to walk through any of this because again, this is, you can just follow along with Ben Eater's programs. I made some modifications to it, but nothing that's super interesting. So here's all the assembly. And then line 690, you can see I go and do the second pass of the assembly. Line 700 through 740, all I'm doing with that code is I'm using that to define end ASM, which is the end of all my assembled code. And so I set in this case, I'm not setting P to 8000, I'm setting P to the location where that code is actually assembled in memory. Because what I'm going to do in the subsequent code is I'm going to iterate from the start of where I assembled the code until the end of assembly and just send the bytes straight from actual memory in this case over to my EEPROM programmer. And so basically at the end of line 740, I've assembled all my code. It's sitting in a location of memory. It's assembled as if it's assembled at location 8000 in memory, but it's not actually. And so at this point, I've got everything sitting in memory that I want to send over to my EEPROM programmer. And then starting at line 750, I declare some variables. And then line 820, so on my previous video, you could see I actually did 2 separate programming exercises where I sent one file which just set the start address of the 6502 programmer, which is written to location 7FFC. And then I ran and sent another file, basically, or another set of bytes over to the EEPROM programmer to write the actual ROM data starting at location 0. And in this program, I'm just doing both in the same program because in this case, I'm not doing a general purpose sending program. I'm actually literally just doing this to do my 6502 program. And so lines 830 through 860 are the first 4 bytes that I'm going to send, which is 7FFC is the location in memory where the 6502 processor looks for its first address to set the program counter to. And then 850 and 860 is just the data for that. So you can see it's going to set the program counter to location 8000. And then I call a procedure. So BBC Basic 2, really cool. It's got you can actually define procedures, and I'll show you this procedure later. But so I allocate those first 4 bytes. I send them over to to the Arduino, to the EEPROM programmer, and then I clean things up a little bit. Line 960 is where I start sending the actual ROM data. And so I iterate through basically, so 970, so I'm iterating from the start of where my code was assembled until where it ends. I'm filling up a byte array in line 980. I'm incrementing the number of bytes. And then I'm keeping a sum of those bytes because I'm going to use that for a checksum. And then if I've got 8, which is a maximum I'm going to send at a given time, or I'm at the end of my assembly, then I send the data, and then I'm done. Okay, so that's the gist of the program, and now I'm going to show you the procedures. So I have a reset, which just cleans things up, and then this make header. I'm not going to dive too much into this either, but basically I send a message header before I send a byte array that consists of a message type and the number of bytes that I'm going to send, and then I calculate a checksum, which you can see in 1180 through 1220. That's the exact same code I have in my previous video, so check that out if you want. And then I create an array that is filled with those bytes from the header. And basically that just assembles the header for the message, and then lines 1300 through 1430 are where I actually send the bytes. And so I first call the make header function, and then line 1320, I'm disabling output to the screen and outputting to RS423. That's what setting it to 7 does. And then all I do is print the 3 bytes from the header, and then I print the byte array that I'm sending, and then line in 1390, I am setting it back so that I'm now outputting to the screen instead of to the EEPROM programmer. And basically, if I typed while all this was happening, any characters I type would actually get sent over also. So if you use this code, be careful not to type anything while it's running. And then I just print some status, and then I reset things and start over. What's going to happen now is I'm actually going to run it. Okay, so as you can see, this is the assembly. And so you can see address locations 8,000 is where all of it starts. And you can see the first byte is 4C, and then a 2B, and then an 80, which is a jump to reset. And so I have a label called reset down below, and it's going to jump to that location. And what's really cool is you can see the location of reset. If you look at 4C is the operation, which is the jump. 2B80 is the address, and low byte is first. And so it's basically jumping to location 8002B. Earlier, when I mentioned that you do the 2-pass assembly, this is why, because when you first encounter this code on the first pass, it doesn't know the label reset, and so it doesn't know where to jump to. That gets filled in, and then on the second pass, 2B80 is known, and so it knows to jump to that location. Remember 4C2B80, because when I go to write the ROM, you'll see that that's exactly the first 3 bytes that are written in location. It's actually going to be written in location 0, and again, I'm not going to explain why. That's in previous videos. However, everything will be referenced as if location 8000. And so this will be the exact code. You'll see 4C2B 8000. And then this is the rest of the assembly. And you can see what's really cool in the BBC is that I can literally see the actual bytecode of what got assembled during the assembly next to my assembly code. So very, very cool to be able to see the output like this, and then actually to be able to look at a ROM and see that the output on the screen is exact same stuff that's in the ROM. Okay, so now it has finished assembly, and you can see the last few bytes are 6C, 6F21, which is just a byte array I have with a string that I'm writing to that. And so when I show a demo later, I'll show it on my 6502 computer. It's going to print to the screen, hello, all caps, comma, hello, exclamation mark. All right, so now it's about to start actually sending to the EEPROM programmer. And so now I'm going to switch screens, and I'm going to show you this actual code running. And on the right, you see I'm also sending it over serial to the Arduino IDE. And so you should see the code writing the bytes on the left-hand side, and on the right-hand side, you'll see the Arduino receiving them and processing them. So there it goes. It sent the start address, it sent the ROM data, and on the right you can see in the Arduino IDE the actual code that was received. So as I mentioned, I first send the reset address, which was at 7FFC, and then I send location 0080, and then it's going to write that to the ROM. At 7FFC, it's going to write 0080, and then it's going to send, this is the actual data for the ROM, and as I mentioned, so ignore those first 4 zeros are the address that this is going to start at. So it's actually 8000, but on the ROM it's at location 0, again, for reasons. But then you can see here 4C 2B80. So that was that jump to location 802B that I mentioned before. So the first bytes at least are correct, and then if I scroll down all the way to the end, you see the last bytes are 6C, 6F, 21, and over here in the BBC Micro tab or window, you can see the last few bytes are 6C, 6F21. And so it actually sent the data over to the Arduino, wrote it out to the ROM, and we are good to go. Okay, so now I have put my ROM back in the professional programmer that I bought, and now I'm going to read it out and make sure that the bytes that I expect to got written actually did get written and that I'm not being fooled by my output. So I'm going to read that back out into a file called bbc-rom-out, and I'm going to hex dump that. And you will see there is the code. So as you can see at location 00, you see 4C, which is the jump to location 8002B. In fact, you can even see hello, hello with an exclamation mark over here in the hex dump. And then you can see down here at location 7FFC, reset address 0080. And so everything was written exactly like I expected it to be, and then everything else is EAs, so we only wrote those bytes that we expected to write. And you can see actually it wrote through byte 60 is the last one, and if you noticed in the output from the previous, 61 or 60 was the last location written in the output. So everything is peachy, and now I'm going to throw this ROM into my 6502 computer that I'm working on, and we'll see it actually work. Okay, so moment of truth. Right here is the EEPROM that I programmed. There's the CPU right there, and some RAM and other things in here. But basically, I'm now going to reset the processor, and we're going to see if that hello, hello shows up. I'm going to hit reset now. What do you know? It worked. How cool is that? I gotta say, even though there's no point in anything that I just showed you or did, it was a ton of fun and I would do it again in a heartbeat. And actually, I very much like programming on the BBC Micro. It's really my first real experience with it, and I am loving it so far. Highly recommend.